Welcome back to the Deep Dive. Today we're tackling something, well, fundamental. Concepts we use every day but maybe get mixed up quite a bit. Heat and temperature.
Oh, absolutely. It happens all the time in casual chat, which is fine. But when you dig into the physics or engineering or even just understanding climate, they are really, really different things.
And you found some great material for us.
Yeah, this instructional summary you shared is fantastic. It's incredibly clear on thermal physics, especially good at, drawing that line between heat and temperature so it actually sticks. It really synthesizes it well.
Okay, good. So our mission today, cut through that confusion. We're going to pull out the most, let's say, surprising bits about temperature scales, figure out why water is such a thermal heavyweight.
A superhero, you could say.
Huh? Yeah, a superhero. And look at how things expanding with heat affects, well, everything from bridges to thermostats. By the end, you should have a much clearer picture of what hot really means and maybe why lakes don't freeze solid. Right, let's dive straight into that core confusion. You've got, say, a tiny cup of boiling water, steaming away maybe 100 degrees Celsius?
Yeah, very hot, high temperature.
Then you have, I don't know, the entire Atlantic Ocean in winter. It's freezing cold, right? Maybe just a couple of degrees Celsius near the surface.
Right, much, much lower temperature.
But that huge cold ocean obviously holds way more energy than the little hot cup. How does that work? It feels like a paradox.
It does, and that paradox is exactly why we need to nail down three key ideas: temperature, heat, and internal energy. Your example sets it up perfectly.
Okay, let's start with temperature then. The boiling cup has a high temperature. What's that number actually telling us?
Temperature tells you about the average kinetic energy of the molecules inside something. Think of it like average jiggle intensity. Are the molecules zipping around fast, spinning quickly, vibrating hard?
Right.
If yes, then the average energy per molecule is high and the temperature is high. That boiling cup, its water molecules are incredibly energetic on average.
Ah, okay, average intensity. So that the cup wins on intensity per molecule. But the ocean, it just has so many more molecules.
Yeah.
Which brings us to internal energy.
Exactly. Internal energy is the total sum of all the energy, kinetic, and potential of every single molecule in the substance. So the ocean has an absolutely staggering number of molecules. Even if each one is moving relatively slowly, low average energy, low temperature.
The grand total energy is enormous.
Colossal. It completely dwarfs the internal energy of the small cup just because of the sheer amount of stuff, the mass.
Okay, that distinction clears things up a lot. Temperature, average intensity. Internal energy, the total amount in the bank. So where does heat fit in? Is it just another word for internal energy?
No, and this is crucial. Heat isn't something a substance has. Heat is energy in transit. It's the process of energy moving from one thing to another.
Only when it's moving.
Only when it's moving, and specifically because there's a temperature difference, energy naturally flows as heat from a higher temperature object to a lower temperature object.
So if I touch a hot stove,
Yeah.
is the stove giving me heat or am I gaining internal energy from the stove? How do we phrase that?
Good question. You'd say your hand's internal energy is increasing because of heat transfer from the stove. Heat is the name we give to the energy during that transfer process. It's the currency being exchanged.
Right. Internal energy is the account balance. Temperature is maybe the interest rate or activity level. And heat is the wire transfer itself.
That's a pretty good analogy, actually. Better than many textbooks.
So molecules jiggling. Is there a point where they just stop, like the absolute coldest possible?
There is. We call it absolute zero. That's 0 on the Kelvin scale, which is minus 273.15 degrees Celsius.
Minus 273.15 C.
Yeah. At that point, theoretically, molecules have the absolute minimum possible kinetic energy. Thermal motion essentially ceases. Quantum mechanics adds a little wrinkle, but for thermal energy, that's the bottom. You can't get colder. The jiggle has stopped.
Okay, moving from the super theoretical to the everyday. Temperature scales. Most of the world uses Celsius. Seems logical, tied to water. 0 for freezing, 100 for boiling. Nice and neat.
It is very neat, based on standard atmospheric pressure, of course. That's Anders Celsius's contribution, the international standard.
But then there's Fahrenheit, which, well, we use it here in the U.S. 32 for freezing, 212 for boiling. Seems kind of arbitrary numbers.
Hey, yeah, the backstory involves brine and body temperature. It's a bit convoluted, but it's Gabriel Daniel Fahrenheit's system, and it's what many people are used to.
The key thing for anyone looking at, say, a weather forecast from Europe versus the U.S. is how much a degree represents. A 10-degree change feels very different on the two scales.
It absolutely does, and this is often overlooked. A Fahrenheit degree is actually a much smaller increment of temperature than a Celsius degree.
How much smaller?
A change of 1 degree Fahrenheit is only 5/9 the size of a change of 1 degree Celsius. So, yeah, if the forecast says a 10-degree drop overnight...
In Fahrenheit, maybe grab a sweater.
Right, but a 10-degree drop in Celsius...
Okay, yeah, break out the winter coat. That's a big difference.
Huge difference in perceived change.
And since heat is energy transfer, we need units to measure that transfer. We hear about calories and joules.
Right. The scientific calorie, that's calorie with a small c, is defined very elegantly. It's the amount of heat needed to raise 1 gram of water by 1 degree Celsius.
Directly tied to water again.
Exactly. It links energy measurement to water's behavior. Now, the food calorie, capital C, is actually a kilocalorie, 1,000 of those small calories.
Okay. And the joule. That's the standard international unit for energy, right?
It is, and the conversion is pretty straightforward. 1 scientific calorie is about 4.18, often rounded to 4.19 joules. Both measure the same thing, energy transferred, whether it's heating something up or, energy from an impact. It's all joules or calories.
Okay, this next bit feels really important, almost like it shapes the entire planet. Specific heat capacity. You called water a superhero earlier.
Yeah.
This is power.
This is absolutely its main superpower. Specific heat capacity, the symbol is usually a lowercase c, is basically a measure of how stubborn a substance is about changing its temperature.
Stubborn. How so?
It tells you how much heat energy, Q, you need to pump into a certain amount of mass, M, of the substance, to raise its temperature by a certain amount, ECT. That famous equation, Q equals MC.
Q equals MCT.
Got it. No, most things we encounter, daily metals, rock, sand, air, they have relatively low specific heat capacities. They heat up fast and they cool down fast.
Like a metal scone left in the sun, right? Gets hot super quick.
Exactly. But water. Water is the outlier. It has an incredibly high specific heat capacity. It's 1 calorie per gram per degree Celsius, or a whopping 4,190 joules per kilogram per degree Celsius.
4,190 joules. Just for 1 degree change in 1 kilogram. That sounds like a lot.
It's huge. Compared to dry soil or sand, it's roughly 5 times higher. That means you need 5 times the energy to raise the temperature of water by 1 degree compared to raising the same mass of sand by 1 degree. Water just soaks up energy without getting much hotter.
Okay, so connect that to the real world. Why does that matter so much?
Climate. Think about coastal areas versus inland areas. Why is San Francisco or, say, Washington, D.C. or coastal Europe generally milder than places deep inside a continent, even at the same latitude?
Because of the ocean.
Precisely. The oceans and large lakes act like giant thermal batteries. All summer long, they absorb immense amounts of solar energy. But because of water's high specific heat, their temperature doesn't shoot up dramatically. They're storing that energy.
Okay, storing it up.
And then when winter arrives, they slowly release that stored heat back into the atmosphere.
So they warm the air in winter and cool it in summer?
Exactly. They moderate the extremes. Inland areas, where the land heats up and cools down quickly because of its low specific heat, experience much bigger temperature swings between day and night and between summer and winter. Coastal areas are buffered by the water's thermal inertia. It's a massive reason why coastal regions are so populated and habitable.
Wow. Okay, so water's stubbornness shapes our climate. What about things physically changing size with temperature? Thermal expansion.
Right. Another unavoidable consequence of temperature changes. When you heat something up, its molecules vibrate more intensely, they push each other further apart, and the whole object tends to expand.
Solids, liquids, gases. They all do this.
They all do it, though typically gases expand the most, then liquids, then solids. But for engineers building things, solid expansion is a constant headache or challenge.
That's the classic example they always mention.
Railroad tracks. Definitely. Train rails are often made in segments, maybe 12 meters long or so. You absolutely must leave small gaps between the ends of these segments when you lay them.
Why? What happens if you don't?
On a hot summer day, that metal heats up and tries to expand. Each 12-meter section wants to get slightly longer, if there's no gap for it to expand into.
It pushes against the next rail.
Hard, with incredible force. And since it can't easily compress the next rail, the track buckles sideways or even upwards. You get these wavy, dangerous tracks. It can cause derailments. It's pure physics in action.
Scary stuff. And it's not just rails, right? Big bridges must have the same issue.
Oh, yeah. Huge bridges, like the Golden Gate or any large span, have very noticeable expansion joints. You drive over them, those metal teeth that interlock.
I've seen those.
They're essential.
Yeah.
A bridge that long might change its total length by several feet, even meters, between the coldest winter night and the hottest summer afternoon. Without those joints allowing movement, the stress from expansion and contraction would literally tear the structure apart over time. Concrete would crack, steel would fatigue.
So expansion is a problem, but can we use it cleverly?
We absolutely do. The bimetallic strip is a brilliant example. You take two thin strips of different metals, say brass and steel, which expand at different rates when heated, and you bond them together, maybe rivet them.
Okay, two metals stuck together.
When you heat the strip, one metal, like brass, expands more than the other, steel. Since they're stuck together, the only way they can accommodate that difference is to bend.
It curves.
It curves. And that bending motion can be used to physically push a switch, closing or opening an electrical circuit. That's the heart of many simple thermostats, like the ones in old ovens or heating systems. Temperature change causes a physical movement that controls something else. Pretty neat.
That is neat. Okay, we've covered heat, temp, specific heat-shaping climate, expansion-shaping structures. What about that water quirk you mentioned, the survival aspect?
Yes, water's anomalous expansion. This is probably one of the weirdest and most vitally important properties of any substance on Earth. It breaks the usual rules.
How so? What's the rule it breaks?
Normally, when you cool a liquid down, it contracts continuously. It gets denser and denser as it gets colder. Water does this too, but only down to a certain point.
Okay, what's the point?
4 degrees Celsius.
All right.
As you cool water from, say, room temperature down towards freezing, it contracts and gets denser like you'd expect, but only until it hits 4 degrees C. That's its point of maximum density.
Maximum density at 4 degrees C. So what happens if you cool it even more, from 4 degrees C down to 0 degrees C where it freezes?
This is the weird part. Instead of continuing to contract, it starts to expand again. It becomes less dense as it goes from 4 degrees C down to 0 degrees C.
It expands when it gets colder. That's backward.
Completely backward compared to most substances. And then, when it actually freezes solid into ice at 0 degrees C, it expands even more. Quite significantly, its volume increases by about 9 or 10%.
Which is why ice floats, right?
Yeah.
Because it's less dense than the water.
Exactly. Ice is less dense than liquid water. Now think about what that means for a lake in winter.
Okay. The cold air cools the surface water.
Right. As the surface water cools towards 4 degrees C, it gets denser and sinks. This mixes the lake water. But once the surface water cools below 4 degrees, it becomes less dense than the slightly warmer 4 degrees water below it.
So the coldest water, between 4 degrees C and 0 degrees C, stays at the top.
It stays at the top, and when it hits 0 degrees C, it freezes into ice, which is even less dense, so it forms a layer on the surface.
And that layer of ice, it insulates the rest of the lake.
Precisely. It acts like a protective cap, shielding the water underneath from the freezing air temperatures above. Because the densest water at 4 degrees C sank to the bottom earlier, the bottom of the lake stays at a relatively stable 4 degrees C, even when the air outside is far below freezing.
Wow. So fish and plants and everything living down there don't freeze solid.
They survive. If water behaved normally and got densest at 0 degrees C, lakes would freeze from the bottom up, becoming solid blocks of ice in cold climates, killing almost all aquatic life each winter. This strange little quirk of water's expansion is absolutely fundamental for life as we know it in temperate regions. It's all down to how the hydrogen bonds arrange themselves near freezing.
That is genuinely amazing. Just a slight change in physics and the world would be unrecognizable. Okay, this has been a fantastic deep dive. Let's just quickly recap the big takeaways for everyone listening.
Sounds good.
First, that crucial difference. Temperature is the average molecular jiggle, internal energy is the total energy stash, and heat is energy on the move because of a temperature difference.
Got it.
Second, water's incredibly high specific heat capacity makes it a massive thermal buffer. It soaks up and releases heat slowly, which is why coastal climates are generally much milder than inland ones.
Right, the planet's climate regulator. And third, that bizarre but vital anomaly. Water is densest at 4 degrees C, and ice floats because water expands when it freezes. This protects aquatic life by making lakes freeze from the top down.
The ultimate survival mechanic built into physics. So maybe a final thought to leave people mulling over, connecting a couple of these ideas.
Yeah, give us something to chew on.
Okay, imagine you have two objects of the same mass. One is a big block of metal, like iron, which has a low specific heat capacity. It heats up easily. The other is a container holding the same mass of water with its very high specific heat capacity.
Okay, metal block, bucket of water, same mass.
Now imagine you drop both of them from a very high building. They crash onto the ground, and let's say, hypothetically, all the kinetic energy they had from falling gets converted directly into internal energy upon impact. Which object, the metal or the water, would you expect to show a bigger rise in temperature from that impact, and why? Think about their specific heat capacities.
Ah, interesting. Connecting impact energy to temperature change via specific heat. That's a good one to ponder. Thanks for that. And thanks for breaking down this thermal physics for us.
My pleasure. It's fascinating stuff.
We'll catch you next time for the next deep dive.